So I met Prokhorov maybe first in one of these Vilnius conferences, 1982. And later on in the Tashkent first international meeting of the Bernoulli Society, he organized, I guess that was his doing, if I understand that right, in Tashkent. So then he was visiting us in Bielefeld a number of times in the 90s, and end of 90s, we celebrated at my home his 70th birthday. So the reason was he was visiting Bielefeld, and he was a little bit afraid of all these celebrations going on in Moscow if he would stay in Moscow. So he said, okay, let's do that in Bielefeld. So we did that in my home there. This is another photo when he was in the 2000s in Bielefeld. I guess he lectured there on Benford's law. That is something on the fractional distribution of numbers, and it can be very nicely used to indicate some falsification of numbers in tax records and other statements involving a lot of numbers. And he was very fond of that and had some very nice results on that. So that was in March 2006. And around that time, we sat together and started with Willem van Zwet from Leiden University to collect some of Prokhorov's memories about his time as a young scientist, as we heard from Albert, when he was starting rather early at Moscow University. And he told us nice stories about how he got a professor and then went to this academy meetings. And so you had to pass a clerk room and to get a gown. And so the clerk at the gown center didn't want to let him in because he didn't believe that such a young guy was already belonging to the row of established professors. So he had wonderful stories about his first time, and we put them together and published that in Theory of Reality. This was one of the last meetings I had with him on occasion of a conference here in Moscow. So we had many conversations about various things, and I was always surprised to see that his range of interest not only was concentrated on probability, but he was knowledgeable about many other fields of mathematics. He was, with all rights, I guess, for some time, the representative of Russia in the IMU, the International Mathematical Union. So he had broad interests and followed a lot of fields of mathematics. Okay, I was very sad to hear then his passing in 2013. Now, what I would like to talk about is something about recent interest. At the end, there will be a small mentioning of Prokhorov, one of his early theorems from the 50s, but these first things are probably not so much around Prokhorov's interest, namely that concentration bounds in high dimensions. Here I will give some examples of recent work on Euclidean spaces and spheres. Why spheres, I will explain. And then some extension of that to something which looks a little bit easier, but has, of course, in terms of applications in digital science, as we call it today, maybe things on discrete spaces, and extension of that. And then I will come to a very old topic, entropic Poisson convergence, where he worked on in the beginning of 50s. And we will use some kind of new distances which are very strong compared to the classical and established ones, that is information distances, and I will review some recent results. Now, what is concentration of measure? So a very nice way to get it is by looking at probability measures which satisfy a so-called log-Sobolev inequality with a certain fixed constant. That means for all bounded locally Lipschitz functions, you have the entropy of the function squared under this measure being bounded by the L2 squared norm of the gradient with this constant. And now the Nabla F norm is now a generalized gradient. In the differentiable case, you can take the gradient vector and its Euclidean norms, but there is also other more generalized ways to use it. And this is a very old subject, starting with Sudakov, Millman, Schechtman, then in the 80s and 90s, Talagrand and Ledoux, which just tells you if you have a Lipschitz function with bounded Lipschitz constants, you're going to have, by the so-called Herbst argument, exponential inequalities out of in a few lines. Now, what we wanted to do is look at cases where you don't have bounded Lipschitz functions. That is, you have functions which are in some sense Lipschitz, but with unbounded coefficients, constants which grow with the observations. So you have something like polynomials, for instance. And there are some previous work by Adamczak Wolf in that region, and also some work we did in 2017 for second order Lipschitz, so to speak, second order derivatives on the sphere. So the idea is basically you do some differencing when you look at Lipschitz of higher order, and now you, as the second, third order, you have bounded constants. Yeah? So, and the question is, what type of exponential bounds can you get by such assumptions? Is there something, a general theory you can make? And here is, so to speak, one of the latest things we did that is sort of already jumping not only to higher, to second, but higher order difference. So let's take the simplest case. We have a d times differentiable function on an open subset of Rn. And now this defines a hypermatrix of d-fold partial derivatives, a lot of functions. And we have to introduce now some norms on those partial derivatives. And one norm is, one norm here is the Euclidean norm of all these coefficients, called Hilbert-Schmidt norm, of this vector of partial derivatives. Another norm is the operator norm. That is, we take here the derivative in the direction v1 up to vd, and take the maximum Euclidean norm in all these things. Now you say, well, what is the sense of having two norms? Of course, none if you have a finite number n of Rn is finite, and then you have, depending on n constants, which these two things are equivalent. But as n goes to infinity, there's a big difference, and all this theory is actually for n going to infinity to have some concentration of measure in things like n. And then these two measures are not equivalent in the sense. Yeah? So, for probability measure, we now look at these derivative measures or sizes in LP norms, either with the Hilbert-Schmidt one or the operator norm. Now, what are the results? First, let's assume we have a measure, I will give some examples in a moment, which satisfy a logarithmic Sobolev inequality on this Euclidean space with coefficient sigma squared. We have a d times differentiable measure. Now, classical concentration of measure says, yes, if I have sufficiently many observations, then my function is concentrated around its mean or its median to a very good degree, namely in sub-Gaussian. Now, okay, you can assume that the function has mean 0. But here we have higher order derivatives. So what we assume is that we not only have mean 0, but we have also all derivatives being 0. So one can weaken that a little bit, but this is, so to speak, the next natural assumption you make from mean 0 to derivatives mean 0. and up to the order d minus 1. And then we assume that the d's derivative is in Euclidean norm of the d's derivative vector is in L2 norm bounded and in operator norm bounded. Here we assume that it's uniformly bounded in its argument. It's the L infinity norm. And that usually is necessary to get an exponential bound. And what is the exponential bound you get here? What you do is you take f to the power 2 over d. So if f is, so to speak, a polynomial of the order d, this is something like growing like a quadratic form, this power. So it's like if I write a quadratic form there, and this is uniformly bounded thanks to the uniform boundedness of the d's order. Without that, you won't get that in this way, this exponential bound, or you can state that in a exponential tail estimate of this form with the power 2 over d. So if d would be 1, so we would have no derivatives, I would take just a Lipschitz function with mean 0, then I would have the usual Gaussian upper bound, tail bound. Okay, so this is the bound we came up with. Now, you can extend this. This is somewhat a little bit awkward that all the derivatives have to be mean 0. You can, in order to get to this thing, you can just work like with Lipschitz function that you take instead of the function minus its mean. And here you would take the function minus some kind of Taylor polynomial in its derivatives. Yeah, so correct it, not only by mean, but by a Taylor polynomial with coefficients coming from the derivatives, and then you are at this result. Now, let me give you now an example. Let's say for just 2 derivatives. We take a Hermitian n by n matrix with IID entries, mean 0, and look at the vector of its spectral values. So, now assume that, for instance, the entries of this matrix are random variables which have the logarithmic Sobolev inequality property. Then this vector of eigenvalues also has a log Sobolev inequality. So it transfers from the entries to the matrix to its spectral values. Another example of log Sobolev is if you take a continuous example extending the usual Gaussian and the complex Gaussian, the real Gaussian, and the quaternionic Gaussian ensembles, as they are called, you take the following Hamiltonian. It is the sum of potentials in the eigenvalues, strictly convex potential. For instance, it's a square. And here you take something like the log Vandermonde or the logarithmic interaction between those. Now, the consequence of the assumption that V is strictly convex potential, and this I have the logarithmic interaction here, is that this Hamiltonian is also convex. The second derivative is strictly convex, is bounded by a multiple of the identity, uniformly in lambda n. And this is called the logarithmic Sobolev inequality, as stated, for instance, and used by Bakri and Emery. And the constant, the logarithmic Sobolev constant, is 1 over n in this case. So this is an example, just to give you one example for things where few examples where this. Now, we want to study now some functionals, and the simplest thing you could study, and that has been done, are functions, sums of these eigenvalues. Now, this behaves a little bit different than the classical central limit theorems we have seen in the first talk, because you won't see a normalization here. The point is that if you order these eigenvalues, they come at very small distance. They are really orderly packed. They don't have much variation from the j's to the j's plus 1's eigenvalue. There's So they are more or less at their quantile places. And that's very different to the sum of random variables. Yeah? So it's only a little bit of randomness if you order them. And because there is so few randomness, you don't need an ordering. It's so-called self-normalizing. And you have nevertheless, the sum converges to some normal distribution, assuming that you have integrable derivative. There's a little bit less stringent conditions. You need only H1 or something like that. Now, if you assume now not only that this is going back to Pasteur, Johansen, and the measure concentration to Gioni and Zaituni in the 2000. Now, if you now assume that you have a second derivative uniformly bounded, can you somehow go make an example out of this second order thing? Yes, of course. You take the sum, the first sum, and now you do what I told you. You take the recentered eigenvalues and multiply by the expectation of the function, derivative of the function at those eigenvalue points. Now you have recentered the whole thing, so to speak, to have the mean next derivative to be 0. And thanks to that, this has now, and you see now you have a factor square root of n here, whereas in the original central limit theorem you had no normalizing factor, so it's of the next order. It's small of the next order what you get if you recenter. And you have still you have still an exponential inequality of this type. So this is a concrete example how you apply these general theorems. Now, let's make an argument for why should one use the sphere. Now, the uniform distribution on the sphere, this is a very old theorem from the 50s, satisfies a logarithmic Sobolev inequality also with 1 over n minus 1. And if you now study d times differentiable smooth function on an open neighborhood of the sphere, now in order to avoid going really into intrinsic notions of covariant differentiation, etc., on the sphere, which are cumbersome, I just take the liberty to embed the sphere in the Euclidean space and taking notions of differentiation in the embedding Euclidean space, which makes life much, much easier, right? So in that, we embed that in the neighborhood of Sn minus 1, and then we say, okay, we have mean 0, and now let's say relax a little bit. We take the operator norm and bound the case operator norm and take the mean of it, and this should be rather small. Should not be vanishing, but rather small. Then the D's operator norm is uniformly bounded on the sphere, and out comes now with a factor n minus 1. So this is small of order 1 over n, so to speak, exponential concentration result on the sphere for this differentiable function. Okay, now I will give you a few examples. Now this sounds like rather theoretical. Yeah, who needs the sphere? Must be very special. But let's see. First example, take weighted sums of coordinates on the sphere. Yeah. So we have the Q's power of coordinates with some coefficients. Let's say the mean, the sample mean of the coefficients is 1. And then you have automatically from this result, let's say for the third power, you have a nice exponential bound with exponent 2/3. If you subtract now, again, from, let's say, the fourth power, its mean, and then you see this is small of order n to the minus 3/2 already, and you have exponential bound. If you don't do that, you see you get an additional factor square root of n here. And if the maximum of coefficients are smaller than 1. So you can really look at these polynomials on the sphere and make exponential estimates for them. So, applications. What you could do is, for instance, look at weighted empirical processes. You have IID variables, you take the classical empirical process, but with weights. And weight theta, and you take the weight theta from the sphere. And the observations IID from P. Then you can look at functions of the weighted empirical process, differentiable functions, and consider it as a function of the weights. This is now, under the IID assumption, a symmetric function. And now we have proved some time ago that a lot of these symmetric functions, differentiable symmetric functions, under such conditions have a nice representation. There is an expectation, which is the limit as n goes to infinity. There is some quantity with derivatives, which is also as the limit goes to infinity of such things, with a third power, and then there is an error term with a fourth power. So as soon as you have symmetric functions on the sphere with spherical, you have this structure. So the sums of powers are not so special, they are rather generous once you have symmetric functions. And of course, you have a concentration of measure result here that this is of order 1 over n exponentially. Now, another one about spheres. This is more in the vein of research of Sudakov. You take sums of random vector elements and take arbitrary coefficients, but you normalize the coefficients to be from the sphere. And the question is, under what conditions can I say something about the limit distribution of that if I take the coefficients generically, for instance, from the sphere? And so there is a nice theorem which does that to a very high precision. If you say I have a vector of x1 up to xn, which is isotropic, has, so to speak, mean 0, covariance 1, identity, its distribution is log concave, and it's coordinate-wise symmetric in its entries, which means that if you take these linear combinations, it's actually a linear combination of the absolute values of x1 up to xn times some Rademacher, which are independent of the absolute value. So intrinsically, this is a non-IID Rademacher sum with all these random values in there, random sizes in there. So there is some strong independence in the sum, although it's not so formulated. But now, looking at the dependence now on these weights is a nice estimate of this distribution of this term in the Kolmogorov distance to the normal one. Namely, the bound is the sum of the fourth powers of the coefficients. You see, they come in naturally in this way again. And in particular, we have the expectation of this Kolmogorov distance is of order 1 over n, and we have a large deviation of this Kolmogorov distance depending on the weights around the normal with order 1 over n. This is a very nice result. Now, it still depends on this coordinate-wise symmetric, which is somehow, as I outlined, some independence of Rademachers, which is hidden there. Now, can you do it more general? Can you do this Sudakov type thing, concentration of measures more general? And here we came up with a condition which says, well, isotropic means covariance of the random components is identity. We're going a little bit further, and we say we take a second order correlation condition. And what this means is we take a quadratic form in the coefficients, and the variance of this quadratic form is bounded by the L2 norm of the coefficient squared. Now, what does it mean, these conditions? So let's first say what are consequences. If x is isotropic with a distribution symmetric to 0, and we have this second order correlation with a finite lambda. Then, taking all these concentration results on the sphere, you see that you can take the characteristic function of this linear combination, compare it to its expectation, and prove a variance estimate where this lambda appears of order 1 over n squared. And moreover, you see a convergence of order 1 over n in exponential ways if you take the mean over all these weights. Now, what is this condition which makes this possible? So if I have a fourth moment, then this lambda, there is a finite lambda already for this thing. And lambda of x can be seen if you take the vector with n squared components of xi, xj, minus its expectation, and take the covariance matrix of this n squared vector, and take the maximal eigenvalue of that. That is, so to speak, a minimal lambda. So we're going, so to speak, to products of eigenvalues rather than eigenvalues in correlation. And if we have that, then we get similar as in Klartak's theorem that the mean Kolmogorov distance to normal is now bounded by log n over n times this lambda. This log n is best possible in this case. Now, we can estimate this, and so raises the question, what is this lambda? Okay, this is one interpretation. A second interpretation for a bound would be it's the smaller than the reciprocal of a spectral gap in the Poincaré inequality for this vector x. So this has a Poincaré inequality, and lambda of x can be bounded like that. Now, if we go to the same class of distributions of x as in the previous lemma, then there is a famous conjecture by Kanan, Lovas, Simonovitz that this lambda 1 is uniformly bounded below, uniformly in n, for all isotropic log concave p measures. So if we go to this class, then everything is fine once we assume that this conjecture, this independence on dimension is true. Okay, so this is a result where you see how weights on the sphere can be interesting and linear combinations, and you have some kind of generic Gaussianity here. Now, as I said, in the digital age are also functions of discrete spaces are interesting. And here we take just finite functions, and so everything is bounded. Now, what's the interest of exponential bounds for bounded functions? There, the interest is in the dependence on n. Everything is bounded, but in which sense does it depend on bounded in n? Yeah? And in order to do that, you define a rather brutal difference notion. You take just the variation in the i's component. Take the difference when I vary the i's component, it's a bounded value, and I call it a bounded operator eta i, eta I in this case. So once you take this derivation, or this difference, then the resulting function of the remaining variables is constant in this variable, which is nice because then you can iterate this L infinity difference with respect to other arguments, and you don't have, you always have zeros on diagonal elements. Again, like in the differentiable case, you get a whole lot, a large vector of such differences, the hypermetrics. You define now LP norms of the Hilbert-Schmidt. I only take here the Euclidean norms of that because that is the only way we could go for this discrete case, and takes the LP norm of the Euclidean ones. And now let's start with the simplest case, namely the independent random variables. So I have discrete independent random variables, or non-discrete, and I can modify now log Sobolev in this way by replacing the gradient norm by this difference, the norm of the difference components, okay, which is always defined. And what I have is, I have always, with respect to this brutal differencing, I have always a finite log Sobolev inequality with a finite constant. It's trivial in this case. So I don't have to worry about this in this case. But the more interesting cases is if I can do such a conditional bound instead of this one here, what calls this tensorization with conditional distributions given xi, then I can drop maybe the assumption of independence in the vector. And that's what we were gonna do. We go for such sub-exponential bounds. Again, we take a function, bounded function, mean 0. Now we take the Euclidean norms of all the differences up to order d minus 1 and bound it by 1. Which means that since there are a whole lot, each one of them is very small. Each one of them is very small. And then we take a uniform bound, not a mean bound, not in the mean squared bound, a uniform bound on the highest derivative. And out comes with absolute constant, again, an exponential bound. Yeah? So you have an exponential bound, in this case with fixed constant, and this is improving previous results by Boucheron, Bousquet, Lugosi, Massin. And you can now work with these exponential bounds in this case. What are examples? Now, one of the classical examples is, of course, bounded Höfting kernels. So I have an expansion, an L2 orthogonal decomposition of a function into functions of 1, 2 more variables which are orthogonal in L2, and I call this coefficients F0, F1, etc. And this is an orthogonal composition, and if this Fi, for instance, is an ice order polynomial, then in the previous case, this last conditions implies the previous ones. And special cases are, of course, Rademacher variables here. And there is sufficient, this condition for the highest derivatives are sufficient for this exponential bound. Now, you can extend this now, in many cases, to polynomial chaos and suprema. So this is, you take a sum of products of this plus minus 1 variables, for instance, called Rademacher chaos, with some appropriate conditions depending on the coordinates you take a multiple of. And for instance, if you have degree 2 here, then it's a quadratic form. You take the supremum over these quadratic forms for coefficients in a compact set, and you take a quantity which is the operator norm of this coefficient matrix over this compact set. Now you can extend that in a very complicated way by taking operator norms about partial arguments here, which is VWK, which I won't really say. But then in terms of these these quantities, you get the following. First of all, you can estimate the P norm of F minus expectation of F in terms of these quantities WK. And you get a concentration result, which is, so to speak, multi-type. It involves a minimum over exponent t squared divided by 2, t squared divided by 3, up to t squared divided by d with these coefficients involved. And you take the minimum of that. Now, in this case, we don't subtract anything. We take the full unprepared functions without subtracting lower order terms. So the exponential result is now multi-type. Depending on the size of T, I get either sub-Gaussian or I get here, on the size of these quantities, I get sub-Gaussian or I get exponent 2 over D. Yeah? So in that way, we can treat rather general bounds. One application is for spin variables. So if I take an extended, for instance, a simple Ising model with a matrix J with sigma I and sigma J, then in the case of high temperature, where I have a logarithmic Sobolev inequality, so this matrix is in some ways nicely bounded, I can get, as an application, if I have, let's say, a higher order matrix here or tensor of the spins, and I have these bounds, I get a bound for this, under this, for this dependent model, this with the Boltzmann factors here. I have also for the dependent model, I can get concentration bound. So there is something, an argument done by Martin behind that in order to, and the approximate tensorization property I mentioned before to get to this. And of course, classical applications can be also done, like U-statistics which have been done by Genet and de la Peña in the 90s. And Peter is probably also an expert in investigating these things of these functionals here. But they all come out in the right order, this extension of Hoeffding's bound. Good. So how much time do I have? How much? A lot. Okay. Then let me come to a classical topic, namely entropic measures, entropic distance measures, and classical results, namely Poisson convergence. So setup is as usual. You have non-identical Bernoulli, independent but non-identical Bernoullis. You take the sum. You take the expectation, which you call lambda, it's the sum of the success probabilities, and you take the probabilities of W and the probabilities of the Poisson and compare it. Now, but you compare it not in the classical total variation distance, but you compare it in a Kullback-Leibler distance. So these are the probabilities of the non-identical Bernoulli sum. These are the Poisson ones, and you also use the Pearson's chi-square type of bounds. And the question is, what will happen to Poisson convergence in these very strong bounds? Okay, there is some kind of Pinsker inequality relating those. That's this total variation is the smallest, then comes Kullback-Leibler, and then comes Pearson's chi-square. And now you can even generalize those again by dividing alpha after Rayleigh alpha divergences. You instead of alpha equals 2 and 1, you take a general alpha. This is alpha Rayleigh, and that is sometimes called alpha Tallis. And you have some relations between d alpha and t alpha by this monotone function, which is non-discreasing. And you see that, okay, if d alpha is equal 1 is Kullback-Leibler. T alpha, if alpha is 2, is Pearson's chi-square divergence. So this generalizes the previous ones. Okay, and now what are results? There are a lot of results. I guess some of the, probably I don't know whether he was the first one to investigate the sum of squares. This lambda 2 is the sum of squares of probabilities of these Bernoulli, the success probabilities. And so Prokhorov was one of the first to estimate that. Later on, de Lecam used similar related bounds in 1960. Then there are lots of papers going that, giving lower and upper bounds by Barber, Hall, Kersten, Chen, and many, many others, which I won't have time to cite here. So you see now this lambda 2 is modified by 1 minus e to the minus lambda divided by lambda by this factor. Then I have, for the Kullback-Leibler, there is Kutyans and Johnson results where you have the third powers of success probabilities. And Pinsker will give you, as I said, the Kullback-Leibler is larger than this squared. And now what we are heading for is the Kullback-Leibler being bounded by some function of lambda like here. Here we have one function of lambda, 1 minus e to the lambda, times lambda 2 squared. Now for the chi-square distance, there has been some more recent work by Zakharovas and Wang and Borisov and Borosenkon, 2008, when the lambda 2 is always, of course, smaller than lambda. And lambda 2 is equal to lambda only in the case when one success probability is 1 and all the others is 0. So a total degenerate case. Otherwise, right, lambda is smaller. And is it smaller than lambda 2? The smaller it is, the relation of both, the more regular the distribution of the success probabilities will be. Right? So, and here if we have lambda 2 divided by lambda smaller 1/4, we see this lambda 2 over lambda squared as a bound. And what we did, we took now things a little bit to the extreme in this way, that we wanted to have also extreme cases of distribution of success probabilities covered by some bounds. And so we use here lower and upper bounds on probability measures with some given absolute constants. And the result is the following. We introduce now a certain function of lambda and lambda 2, which is more or less if lambda is smaller than 1, lambda over lambda 2, lambda minus lambda 2, this f. And then we have an equivalence, lower and upper bounds with constant of lambda 2 over lambda squared for Kullback-Leibler with 1 plus log f. And for this Zallis, which is the chi-square for alpha equals 2, with f to some power alpha minus 1 over 2. Now this now covers, you see I've made no assumptions about lambda or lambda 2 and their relation. So it covers all the, including all the extreme cases. And if I now do applications of that, let's say for lambda smaller than 10 and lambda 2 divided by lambda smaller than some constant c, or for instance maximum of these things smaller than 1/2, then I get to an equivalence. Under all these conditions, I get an equivalence of Kullback-Leibler chi-square to lambda 2 over lambda squared, which is in this case then z. Now, what we do is a little bit different in many techniques. There's a Stein-Chen technique, there is coupling techniques. Lots of things can be done for these discrete probabilities. We used complex analysis to really contour integrals to try to cover the extreme cases. And so here on the lower bounds from Barber-Hall, you see this is 1 over lambda squared is certainly something you get as lower bound. And if you go to extreme cases for lambda and lambda 2, then you see if you get this log factors coming in. In this case for D, and here this for chi-square, you get this type of factor. Now, there is one way which is rather recent to go to another even entropy difference is by just looking at the Shannon entropies. The Shannon entropies of the distribution of a sum of non-identical distributed Bernoullis and the Shannon entropy of the Poisson with the same mean. Okay. So here I wrote down the two Shannon entropies, and I take the difference. Now, why is this an interesting quantity? Now, it has been shown, and that was a conjecture for a long time by Shepp and Olkin, being proved by Hillian and Johnson, 2017, that the Shannon entropy of the sum of non-identical Bernoullis is indeed a concave function of P1 up to Pn. So you can take P1 up to Pn equal, and which ends where you end up with a Poisson case, and so you have a positive difference, which you then can interpret as a kind of entropical distance between both. And, well, we could apply our methods. So this positive difference is an informational distance. And you can apply that and get lambda 2 over lambda with a factor c lambda. And if we don't have two extreme cases, this c lambda is of some kind of logarithmic dependence of lambda with an absolute constant. So you see, if you go to different distances, stronger distances than the classical total variation, you can, even in these classical theorems, get some interesting new ones, which also cover more extreme cases. And with this, I would like to thank you for your attention.
Thank you very much for this very interesting talk with many, many nice examples. So it is time for questions. Are there any questions? So, just a moment.
Prokhorov and Likan.
Yeah.
You say that the Prokhorov 53, it was 52.
52 even. Ah, okay.
No,
thanks.
because in fact it was his dissertation.
Aha.
It was candidate dissertation. I'm saying this simply because the meeting, Prokhorov meeting. And also in this connection, I want to say the following. No, definitively, Kolmogorov made a lot for Prokhorov, but Prokhorov also was used by Kolmogorov. In '56, Kolmogorov wrote papers, two theorem of theory of probability about approximation of random variable by infinite divisible random variable. But in Prokhorov inequality, binomial distribution is not infinite divisible, but Poisson distribution is infinite. It is a discrete case, and Kolmogorov used it in his paper in the '56. And in this paper, as I remember, there are only 3 references: Dublin, Levy, Dublin, and Prokhorov. Levy, because, how to say, function of concentration, and Dublin, no, and he used Prokhorov results exactly this one.
I see.